Hello. Let's talk about earthquakes, big earthquakes, the kind of things that come along rather rarely. Similar to a pandemic. It's a big, bad thing that comes. You know it's going to come, but you don't know when. Now, for California earthquakes, 1906 San Francisco, a huge one. But then it was 83 years until we got to 1989 before southern San Francisco was hit. A little over 4 years later, Northridge. But now it's been almost 28 years since a major urban area has been hit with an earthquake in California. That means a whole generation of people have come to pass. In this last 28 years, 8.5 more residents in California. So what I'd like to do tonight, or this time, is look at a few historic earthquakes for lessons that we can bring back to San Diego, and our focus is going to be on big earthquake in San Diego. Now first, a regional tectonic setting map here. When we go way down here to the Gulf of California, what we're going to do is we've got the whole west of North America here, but here what we have here is spreading. That is to say, that green arrow, what it's showing us is the Earth's being torn apart. The left side of the arrow, pointing out of the Pacific Ocean, that is what has taken and pulled California away, and we're moving on up through the San Andreas Fault. And you see that 5.6 number right in the center of the circle there? That's 5.6 centimeters a year. That's saying that's the amount of movement that's being fed into the San Andreas each year, almost 2¼ inches, but we don't release it every year. We stop, we save it up until we get a really big event, and then it moves. So what we want to do here then is look a little bit more at our part of the world. And when we look here at Baja California, if we look at the tip of it, we can see where we can see this pull apart right here. We see that the tip of Baja California is 300 miles separated from the state of Nayarit at the other end of the arrow. If we move on up into our part there, we can see that the state of Sonora and San Diego would have been connected. That is to say, if we removed 6 million years worth of movement, that is, in your mind, take San Diego, take the Baja California Peninsula, and slide it back down towards the right so there's no Gulf of California, then in a modern political sense, San Diego would be part of the present-day state of Sonora in Mexico. But the other thing I'd like to focus on then is the San Andreas, and we see all this movement. And here the red, you see that is the southern end of the San Andreas Fault. Notice that it ends just before the end of the Salton Sea. And then it moves on up through the state. And it says San Andreas cuts across the landscape in spectacular fashion and feeds on up all the way up until it goes offshore in Northern California. Now, let's look at the big earthquake history on the San Andreas Fault. First, let's go back to 1857. This is called the Fort Tejon earthquake. And if you think back to California history, the big rush of immigrants came in chasing gold after that strike in 1849. So here's a big earthquake only 8 years or so after the great mass immigration began. But this particular fault, the San Andreas, this particular earthquake, the Fort Tejon earthquake, occurred on January the 9th in 1857. 220 miles of ground surface were ripped. It was a magnitude 7.9 earthquake, and the offsets in some places were up to 31 feet. That means if you took a corral, for example, you could split it and cut it in two and separate it by 30 feet. Following 1857, the next big one is 1906 San Francisco. That's the famous one. I think probably maybe the most famous earthquake in the world. And that one, the ground surface ruptured for 240 miles, up to 20 feet or so, and, well, a huge event. So what's been missing is our part of the world, all the way down here at the south. We simply haven't had all this kind of action yet. In fact, when we dig into the sediments and look at it, it looks like the last big earthquake in this part of the world was around the year 1690. So this isn't pure science, it's more just looking at history, but you might expect that the next big earthquake here in California might well be the San Andreas near us. Now, if we look at all the faults here, again, the Mexican border at the bottom of the diagram, and you can see the San Andreas Fault, how it runs up, bends, runs on up. There's the San Andreas, and to its left is the San Jacinto Fault. And if we move over one more fault, there's the Elsinore Fault, and then the Rose Canyon Fault running right through the heart of San Diego. We're going to be talking a lot about that because ultimately the bulk of this talk is going to be about earthquakes in San Diego. I can't help but show this, to me, beautiful piece of art, the kind of thing you like to hang on the wall and look at, but this is pure science. What the ribbons you see there, each of those ribbons is a fault, and they're about 10 miles deep. And then the different colored segments, those are the portions of the fault that moved in historic or prehistoric earthquakes. And then you see a lot of clusters of aftershocks and things in there as well. So that beautiful artistic representation. But when you look at it, look at San Diego. We have several faults going through here. Look at Los Angeles, though. Oh, my goodness. They've got them north, south, east, west. They've got ones buried below the surface you don't even see. We're better off here in San Diego, which is not to say we don't have things to think about. Now, a couple of lessons. The Landers earthquake, you may remember that one in 1992. What we have with this particular earthquake, if we look at the map, you'll see down near the bottom there, you'll see the star representing the epicenter of the earthquake. And what we basically kind of thought is, if you look right here, we're covering the Johnson Valley Fault, and you notice it ends, and then we move up to a Homestead Valley Fault. Well, the thought had kind of been that once one of these faults, like visualize Johnson Valley, starts ripping and moving, when it gets to the end of the fault, that the energy would disperse and wouldn't carry over to other faults. But what we saw there in 1992 was the Johnson Valley Fault went end to end. Then it jumped over to the Homestead Valley Fault, which went end to end, then jumped to the Emerson Fault, which went end to end, and then to the Camp Rock Fault, and stopped in the middle of the fault. Not what we expected, but that's Mother Nature. She surprises us. We watch her to learn from her, but the reason for bringing this up right now is we're going to bring this back to San Diego. We're not going to just look at a fault segment and say, that's it, an isolated entity. We're going to consider that movement could jump from one of these to another. And I couldn't resist putting this up just for general understanding of fault movements. Now, when you look at this, way up at the top here says ground surface. So the black line on the top here is simply the ground. But if we come back over here to the left and go down, we're going down in depth in kilometers, so we're almost 10 miles deep. So the idea is here, you're looking at the fault wall, and notice that the fault moves different amounts. If you look in the center of the diagram right there, the bullseye, there's a 6. That's meters. So that's like 20 meters of horizontal movement there. But if we move over here, look, it's only 2 meters, 7 feet of movement. And I guess why I'm showing this is to give you more of a physical idea of how a fault moves. It's not just a smooth thing where everything moves the same amount. Look at that pattern. There's areas there that are colored in red where you could say almost all the strain energy has probably been released, but then you look at some of these other areas where it's 2 or areas like this and say they could still have a lot of strain energy stored there. Another earthquake could occur sooner than one might hope. Now, here's a familiar one. A recent one, that is to say, Ridgecrest, remember that July 4th and July 5th earthquakes? I wanted to focus on one thing. Again, there's a mental picture from this that I want us to take back to San Diego. And if I take this picture of the ground here, to me this is just stunning. So feast your eyes on that a little bit, and what we're looking for here are multiple fractures, multiple faults. And notice maybe one way to orient from the top to the bottom in the middle there. Do you notice a road? And you can see that road is offset. And then look, cutting across that, you can see there's the main fault branch. But the thing is, it's not just movement on the fault. When you look at this, start down here in the lower left, look how chewed up the ground is there. Look at all those fractures. Look at all those bits of movement. We can look how many there are. I mean, it takes time to count them all, map them and count them. Look at all this ripping tearing apart of the ground surface, some places torn more than others. And the mental picture I want is just this. How about if we came to San Diego and visualized there was a subdivision of homes on there? It's not just a home right on the fault, but neighborhoods can be broken. And by broken, I'm referring to the concrete slabs, the foundations you're on. You could crack one of those slabs and water doesn't come in and out, or natural gas. You can do a lot of damage just by having the ground shift for you a lot. Now, I'm going to show you an old diagram next, just for a few seconds, just for the heck of it here. But all these black lines you see running over the heart of San Diego, those are faults. And in a way, I was wanting you to take the picture we just looked at and bring it over here as an idea of worst case scenarios. Now, one of the ways we rate earthquakes is not just on the magnitude. That's the familiar thing. You know, we say, oh, it's a magnitude 6 or whatever. That's significant. Another thing is the duration is shaking. But what I want to carry forward with here now is the next three aspects of an earthquake. How far away were you from the epicenter? How far away from the original fault movement? What kind of material are you on? Are you on mud or sand or hard granite? And construction style. Is it a tall building? Is it made out of wood? Is it made out of bricks? Let's look at those three factors in a couple of earthquakes and then take that observation, those observations, bring them back to San Diego to get some idea of what we might expect. Now, first here, this is distance. What we're looking at here is the We're looking at the San Fernando Earthquake back in 1971. So there's the red bullseye. And as you see going out from that, you see the intensity of the shaking goes down. And I think that's what you'd expect. The farther away you are, the least problem you expect. However, as you've already just had a preview, here we are now in 1985, September 1985, and we're looking at Mexico City. Mexico City, look at that, 250 miles away from this rectangle, or this oval right here. See where it says September 1985? Then this dashed black oval, that's where the fault moved. And then Mexico City is 250 miles away. And if I tell you an earthquake is going to occur 250 miles away from you, that doesn't fill you with fear, I wouldn't think. But what did it do to Mexico City? We have massive building collapses throughout the city on the order of 10,000 people killed. But I want to dig into this a little bit deeper. It's not just everything destroyed. You notice that I have shown here, it says up at the top, a 15-story building. Well, most of the destruction was in buildings 15 stories, 12 stories, 8 stories high. Short buildings, not so much. Really tall buildings, not so much. So in other words, the size, the height of a building was significant. And what we're going to find is that in seismic waves, and we'll talk about this a little bit more when we have a seismic wave pattern, why would it pick on just certain size buildings in particular? Here, we're up in Watsonville, California, and I just put this picture up here because I wanted you to see liquefaction. Can you kind of see that wet sandy area? It looks like you've had a lot of geysers there, doesn't it? Like almost like volcanic eruptions where water came gushing out of the soil during the shaking of the earthquake. So soft, weak foundations. Now, if we go back to Mexico City, the first thing I'd like to do here is go up here to the top where UNAM, that's the National University of Mexico. So the red line you see, that's the amount of shaking that was recorded there at the university. And with the university, they're on volcanic rocks, lava that had crystallized into hard, solid rock. They didn't have much shaking. But I don't know, have you traveled to Mexico City? Have you gone to places like the floating gardens at Xochimilco and seen some of those soft, gooey muds, how messy they are? Well, here's the exact same earthquake, but look how the mud amplifies the shaking. This is the same seismic waves. This is the same earthquake, but look what the soft mud does to them. The soft mud makes them move up and down much more. So now we're identifying building sizes and also different types of foundation materials. Now, I want to move up to the Bay Area, and we want to look at that World Series earthquake here from October 1989. And just a little advance about coming attractions here. I have put in bold 6.9 magnitude. I put it in bold for a reason. We are going to come to San Diego, and we're going to see how it has been agreed after years of discussion among geologists, seismologists, structural engineers. What is a maximum, not maximum, what's a large-sized earthquake that's reasonable to expect for San Diego? And the number agreed upon, I can say it unanimously, is a magnitude 6.9. Now, I emphasize that now because we're going to look some of what happened up in the Bay Area in 1989 and then take some of those mental pictures back down to San Diego with us. So first off, near the bottom of the map, let's bring in the San Andreas with its movement. So colored over on the diagram in a lilac is where the fault moved. I brought the green arrow in there. But the other thing I'd like to show is the arrow pointing towards Santa Cruz. So there's a city sitting right next to the earthquake, nearby. Now I want to move on up farther and look at Oakland, 60 miles away. So what we want to look at here are the different kinds of buildings that are affected if you're close to the fault movement or if you are farther away. And for us in San Diego, what we'll do is we'll look and say what happens for a San Andreas Fault earthquake way out to the east versus a Rose Canyon Fault movement that runs right through the city limits. Now, what I'm after here with this is just a seismogram, the recording of the shaking from an earthquake. It's just a magnitude 5.1. But the point of putting this on here, what we're trying to show is, you notice the shaking is very up and down, very frequent, what we call high frequency shaking. When you look at this high frequency shaking, notice we're right close to the earthquake. So what we're looking at is a lot of this shaking that's just going like this. And what kind of building's going to shake the most like this? Let me introduce the rule of thumb to you. We basically say that the way a building shakes, it's about 1/10 of a second per story. So if it's a 1-story house, you're going back and forth at a very rapid rate. If it's a 10-story building, 10 times 0.1, then you're going back and forth at 1 second. Or we saw that ruined building in Mexico City, 15 stories, that would be about 1.5 seconds. So what I'm showing here first with this one is high frequency earthquake waves early on. So for Santa Cruz City, now up there they called their old historic district the Pacific Garden Mall. And there's a classic problem they face that cities throughout the US and the world do. What do you do about the old historic core of a city? These are great for restaurants, for tourism, for the whole life experience, and you want to preserve them. But they were built without knowledge of earthquake potential. So do you tear things down and build back earthquake safe, or do you try to preserve the ancient history for everybody's enjoyment? Well, Santa Cruz preserved it until the earthquake, and then it all came falling down. 1- and 2-story brick, stone buildings, the worst kind of things to be in an earthquake, particularly when you're near the epicenter of a large earthquake. Now, in San Diego, what do we call that district? Here we call it the Gaslamp District. And I'm not saying the Gaslamp District's all going to fall down, but I'm just saying we'll look at a few buildings a little bit later on, and let's just say that these earthquakes, not mass destruction, but certain key things fall with a sickening aspect to them. Now, I want to compare that nearby, high-frequency, short-period seismic waves. Here's that same 5.1 magnitude earthquake, but now we're 120 kilometers. We're on the order of 75 miles away. And look what has happened. What's happened is those high-frequency, short-period waves that did all the destruction, for example, in Santa Cruz, they pretty well died out. But look what's taken over. What's taken over are these long period waves. Look at this. There's a 2 seconds bar right here. And for one thing, the bigger the earthquake, I'm talking about magnitude now, the bigger the magnitude, the greater amount of energy there is that's stored in these low frequency, long period waves. And what's our rule of thumb here? At a tenth of a second per story, if you're 75 miles away, what's going to be shaken the most? Tall structures. For Loma Prieta, here was the most sickening thing that happened. It was the collapse of the Interstate 880 elevated roadway. What I'm trying to highlight right there is an upper deck. That upper deck was supported by all these pillars, and the upper deck came crashing down on the lower deck, where it looks like it's just one structure now, but 42 people died crushed in that fallen roadway. 32 hunks or slabs of concrete, each weighing 600 tons, came crashing down during that earthquake. Now, the other thing I'm after right here is that was a 60 miles away. So these are the long distance waves, the ones that have the long period between them, the ones that shake the higher structures. Now, I'd like to dig into this a little bit deeper. Here's a map of that same area. And what I want to do first, let's start up here in the upper right with bedrock. This is what the seismogram, the shaking record we're looking at is from this Loma Prieta earthquake, 1989. So here, the red dots showing you're on bedrock, not much shaking. Look at the next one, you're on soft mud. Wow, same thing we saw in Mexico City. The soft mud amplifies the seismic waves and makes them rise up and down much more distinctly. And then the bottom one here, sand and gravel, intermediate. Now let's follow this over here and see at the top of the lighted circle now, the maroon colored road. That is that same elevated roadway, but it's sitting on sand and gravel. The part that was sitting on soft mud is hatchered there in those dashed maroon areas. So what we're saying is the structure, which was inferior, it was built in 1957. It was something that after the 1971 San Fernando earthquake, it had already been 14 years out of code, but out of code means going back and retrofitting. But which part collapsed? It's the same badly built structure, but the part standing on sand and gravel was still standing. What collapsed? The part that was standing on the soft mud. So what we're trying to do here is relate building height to frequency of seismic waves and also to what the foundation materials are. Now let's go to San Diego. First, distant fault movement. So what we'll be talking about here then is that San Andreas Fault we looked at there, where that section, southern section, hasn't really moved since around the year 1690. And a working group got together here. By that I mean many, many geologists, seismologists got together to figure out what would be a reasonable earthquake to expect from this southern San Andreas Fault. And what they came up with is this magnitude 7.8. Now, we've been using this for quite a number of years now. Each October where we have the virtual earthquake, we do the drop, cover, and hold on drill, especially in the schools. This is the earthquake, shall we say, earthquake that one would expect. So specifically what we're looking at here then is, they said, let's begin it at the end of the San Andreas Fault. Now, this isn't science. This is just setting up a scenario, setting up a model. So the star would be the epicenter, and then they say if it ruptures along a 185-mile length up here, through the city limits of San Bernardino, on through Palmdale, that 185-mile long rupture would generate a magnitude 7.8 earthquake. Basically the same size that we had in 1906 San Francisco. Now for San Diego, of course, the good news is it's not running through town. It runs through the city limits of San Bernardino. It's a much more problem for them than us, but what do we get? Well, here with terabytes of data trying to simulate those seismic waves. And so what we see, remember now they started down here and moved to the northwest, moved on up, 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 and you see how much energy there is here at this time. And notice this is 93 seconds, a minute and a half after the earthquake began. Now, you notice then that it's moving to the northwest, and they're shaking much more than Mexicali is on the southeast. We call it directivity. Simple scientific term. The word direct, the direction things are moving, the directivity, you see Los Angeles is being shaken far more than Mexicali to the south. But that was just the assumption. It makes just as much sense to say that the earthquake actually, previews of coming attractions there, makes just as much sense to say that the earthquake rupture begins up here and moves to the south. And now look at Mexicali, Yuma there in the crosshairs. Now take all that high energy you see up there to the northwest, take that and put it down here and see how well El Centro and Mexicali stand up to it. Now for San Diego, you can see the waves going through us. They're significant. These are those long period waves, the things that are 1 second, 2 seconds apart kinds of things. And so I put a few pictures in of buildings in San Diego. I'm not saying any of them are going to fall, but I'm just saying what are the kinds of tall structures on foundation materials that aren't necessarily the strongest, the kinds of things that are liable to shake the most. And I know, these things were designed to withstand earthquakes, so I'm not predicting disaster here. But what we are looking at is to say which kinds of buildings, which structures would be tested the most. Well, how about the bridge over to Coronado? That was built in, unveiled in 1969. It was on the 200-year anniversary of the founding of the first Mission Catholic Chapel here in San Diego. So 1969, but I'm very happy to report that to the year 2003, they spent $100 million on an earthquake retrofit. And for that, I say thank you. Oh man, I much prefer spending that money up front rather than waiting for things to fall down, kill people, and then go try to fix it. But nonetheless, that is a structure that is the kind of thing that would react to those seismic waves. They've tried to engineer now to handle all of that, and I trust they've done a good job. I'm certainly not trying to spread any fear here. We're trying to understand seismic waves, buildings, foundations, how these things work together. Now, if we look across Glorieta Bay there to these residential towers in Coronado, each of those, there's 10 of them. They each have about 140 units in them. Some were built in the late 1960s, some in the 1970s. I guess each one is independently governed. But these are some of these structures, if they all are run independently, some of those in the 1960s were built without the advantage of the enhanced building codes following the 1971 earthquake. Again, maybe they've taken care of these things, I don't know, but I'm just saying those are the kinds of buildings that will be tested. How about the Sky Tower at SeaWorld? Boy, wouldn't that be exciting? To be up there, 320 feet up in the air with all the people up there and then get a little shaking. Not saying it's going to fall, but it's a structure that one would certainly expect to react. Another one of these things here is the Mission Valley Viaduct. The bridge is going across Mission Valley. And again, they're sitting on water-saturated sands in the San Diego River Valley, but I'm also happy to report that we had a massive earthquake retrofit there finishing over 10 years ago, and I'm very pleased about that. One last thing on these taller or these kinds of structures. What do we do here in modern engineering with, we don't want to build these buildings directly on the ground. If the building's sitting on the ground and here's the building, then when the ground shakes, the building shakes. So we like this term here, that engineering term, base isolation. So what you see here is a photograph of one corner of the buildings of the Office of Emergency Services at San Diego County. And you see what they've done there? They've built, well, maybe it's analogous to the shock absorber on your car. You hit a bump, but you don't feel the full bump. Because what do we have here? We have this cushion here of rubber layers in between lead. Lead's the soft metal that deforms. Rubber can absorb energy. And the idea is, let's build these tall structures, not put them on the ground. Let's insulate them from the ground some so they don't shake as much as the ground does. Lots of different designs, a lot more of them going forward in the future, and I welcome each and every one of them. Now let's look at close by, nearby fault movements. So in this view here, we're up over northern Baja California, looking across part of Tijuana, Imperial Beach, San Diego Bay, La Jolla, on up the coast towards Oceanside. And so let's look here at Rose Canyon Fault segments. Here's one segment here. Here's another segment here. Now this southern one is called the Mission Bay segment, and Tom Rockwell assigned a 6.4 magnitude earthquake potential to this one if all 15 miles of it moved. And then the northern section of that, the Del Mar, is 21 miles long, and Tom Rockwell put a magnitude 6.6 on that. But what we're doing now is, now that we're not looking at individual fault segments as truly being individual and thinking that they can connect, again, remember the Landers earthquake? Remember how it jumped from one fault to a second, to a third, to a fourth? Well, it seems like it makes more sense for San Diego to prepare for combining those two, and if we combine them, that's a magnitude 6.9 magnitude earthquake. The same magnitude as happened up in the San Francisco Bay Area in 1989. Now, we're going to come back to this on a second time, but right now I'm looking over here on the right-hand side. There's Rose Canyon Fault moving up in different segments, and then going up into the Los Angeles area, where it's called the Newport Inglewood Fault. Now, look at the upper portion. Look at the upper portion of that fault. And I'm going to remove the yellow. And do you see the line of hills that were covered there? When you drive Interstate 405 going through LA, you know on your left you see, oh, there's Signal Hill, there's Dominguez Hills, there's all these various hills. Those are hills that are squeezed up along the Newport Inglewood Fault. And for San Diego, we have the exact same fault. And what do we have squeezed up along the fault here? Mount Soledad. Same fault, same effect on the landscape. But the reason for bringing up the Newport Inglewood Fault now, it has had a significant earthquake, relatively modern, 1933. Notice that time of day, 5:54 p.m. So important what time of day an earthquake occurs. You think about your typical day. Where's the best place in your typical day for you to be during a major earthquake? Home in bed. And I say that trusting that you don't have a ceiling fan hanging over your bed or a heavy armoire right next to it that's going to fall on you, but with a little space around your bed, there's the safest place you could possibly be. Now, what happened in Long Beach, here we are looking at a map of it, and coming up there, the yellow arrow pointing into where the rupture began, there offshore of Huntington Beach, and then the rupture moved on up as colored over in the black, Newport Inglewood Fault. This was about 8 miles deep. It did not rupture the surface, but still it was a 6.4 magnitude earthquake right in a populated area, and what got hammered? Schools. Man, oh man, what did I say about noticing time of day? 5:54 p.m., hallelujah. 70 schools fell and were totally destroyed. Oh, you hate to even think about that, having 70 schools full of school children. But the legislature, one time the legislature acts is in the year immediately following a disaster. So following the destruction of 70 schools in the 1933 Long Beach earthquake, the legislature passed the Field Act, which ups the building standards for schools. Not for all buildings, but for schools. And again, I'm always in favor of increased standards. Long Beach, just city itself, you see the brick buildings, not good kind of buildings to have near the fault. We see it here in 1933 on, basically this is the same fault that runs through San Diego. We saw what it did, the same situation did in Santa Cruz, what it did to the Pacific Garden Mall. So we don't want these kinds of buildings anymore. We don't want to build buildings that are where the structural support is brick. What we want is structural support to be steel or wood, something that can yield and can move some with the seismic waves. Now here's just some pictures I snapped downtown. Now the first thing I want to focus your eye on are these bricks here with the very rough exterior. So here's what they look like inside. They're hollow. and they are about like those flower pots you get that are that color, that are real brittle and break. So it's a big, heavy brick, but the interior is hollow, and these things crack and fail in earthquakes. But with this rough exterior we have over here, they plaster over beautifully, and you can't just necessarily see them. I can remember walking downtown here and seeing one of these buildings beautifully painted with the gold trim paint and looking great. And then I noticed down here where a truck had backed into a driveway and punched a hole in it. Beneath that plaster was those kinds of bricks. They are no longer legal. We're retrofitting those buildings. There's still some that exist. Some of those buildings where they exist have been retrofitted. Some of those retrofits, frankly, I'm not impressed with. But let's look here at another building from downtown. And I did this to sort of contrast the two kinds of brick types. So there in the center are like those 9-inch long, solid red bricks like we're used to. And then next to it, you see the relative size of those hollow core bricks, what we call URM, unreinforced masonry structures that crack and fall way too easily. Now, I want to move on to a couple of other things. This is not a plotted map. I just put some lines on the map here. You see the Rose Canyon Fault in red coming down and dying, and then some of the elements of it crossing over Coronado and North Island. But what I want to call your attention to right now is to come over here to the south, the Nacion Faults. Now, this isn't a map fault. Roughly speaking, I'm just doing something that's, well, more or less along 805. But what I want to introduce is a different kind of fault, a different kind of action here. And specifically, what I want to talk about is this carries the geologic name of normal fault, which is a horrible name. The significant thing here is if you look in the upper left where it says extension, that's that. If you pull apart the landscape, what's going to happen to the land? Well, some piece has to fall down if you pull it apart. So that's what the Nacion Faults are. See where it says fault scarp in the middle of the diagram there on that little cliff face? For those who can visualize this, ride with me. Cross the Otay Mesa border crossing into the U.S. and get on Highway 905, and then drive 905 heading towards the coast, then you drop down going towards I-5, then you drop down again and drop down again. You're dropping down the fault scarps, faults within the Nacion Fault system. So I want to show it this way here. So I've put in here, here's San Diego topography, ink drawing from 1941. And here's the Rose Canyon Fault. I connected the bend up there. And there's the movement. And then at the bend, there's Mount Soledad squeezed up. And then the main movements go offshore. And those faults, notice the arrows between the two faults. They are pulling apart. There's extension. When you pull apart the landscape, what does the land do? It has to drop down. And what's there where it drops down? San Diego Bay. Now, the story is even more complex than that if we add the time element. I hope you've been to the Cabrillo National Monument there at the tip of Point Loma. If not, please go. You'll love it. But the rocks you are standing on there, if we come over here to Imperial Beach, they are a mile deep. And so when I say the landscape drops, the drop is more than what the eye just sees today, because once you make a hole on the ground surface, then the streams start filling it with sand and mud, and the hole is not totally filled, but partially filled, and we're left with San Diego Bay. So I wanted to alert you to that class of faults as well, and then turn you on to a map here. This is accessible to you. This is, I mentioned a working group talking about what size earthquake should we prepare for in San Diego? And I talked about that being a 6.9 magnitude. Well, this is a composite map of that. You can find this on the San Diego Association of Geologists website. Just Google SDAG. This map will appear, and it's interactive. You can put your cursor on different fault lines or different areas, and more information will come up. So if you want to dig into this a little bit more, there's a readily accessible free resource for you. SDAG, Google that. Now, busy little area we have here. We've talked about the Rose Canyon Fault. Now we're just talking about La Nacion Fault, but we left out so far the third area, the offshore faults. You see these offshore faults out here? These faults are capable of earthquakes in the magnitude 7s. And if we look again at this beautiful rendition of the seascape, what's the seafloor look like underneath it? What I'd like you to do here is just run your eye over this landscape. And well, look at that. See that right in the middle? Look at that. Doesn't that look like a knife cut through there? That's a fault on the seafloor. Here's one over here. Well, you do it with your eye. Look for places. Imagine you had a knife and that's blue putty and you're slicing it up. Do you not see a number of the faults that lift offshore there? Let me put it this way. Each of those islands you see is uplifted by faults. And we're going way up north here. This is the Northern Channel Islands. There's Santa Cruz, Santa Rosa, San Miguel. We're off of Santa Barbara. So we're coming off of Santa Barbara all the way down here to almost to Ensenada. So we're looking at a whole raft of faults out there along the seafloor that we don't talk about as much, I guess, because we don't see them. But they're there, and they, like I said, can easily do magnitude 7 earthquakes. Which brings us up to another thing. What can the offshore faults do other than just shake us? They can also give us tsunami. Now, I'm not saying the magnitude 7 fault movement offshore is going to do it, but I want to go to an event here, relatively recent, 1998 you see there. This is in Papua New Guinea, and I have listed there a 7.1 magnitude earthquake. Well, as it turns out, offshore, way out here, they had the magnitude, 12 miles to be specific. 12 miles offshore, they had a magnitude 7.1 magnitude earthquake. Didn't create a tsunami, but what it did do was shake loose a submarine landslide, and that submarine landslide ran 4 to 5 minutes later, ran a 13-foot high wave across into the bay. Then the water pulled back. A second wave came across, estimated at 40 feet high, and then pulled back, and then a third wave came across. And so what happened along this landscape right here, that this looks nice, barren, and open, well, that's because it's just been cleaned off by tsunami. 2,200 people died there. Now, when I look at that from an offshore fault, 12 miles offshore, magnitude 7.1 earthquake, we have that. Could one of those set loose a landslide, submarine landslide? Could. So that could happen. So when I looked at this, and you know what I saw? I saw, well, if I put a roller coaster right here and a Roberto's taco shop here and so forth, isn't that Mission Beach? So that's another little thing we have here. Now, what I want to do is just go over a few things here that are more specific about our houses, a few of those, and then we'll move on to questions. Now, here's a house in the 1971 San Fernando Earthquake, a photo by Al Boost. And what I want you to notice there is how the vertical elements and the horizontal didn't move together as a unit. And so what we want to do on this diagram here, what I've done, I'm going to show you what we need to do. So I start off here, down at the bottom, I've drawn the cement slab, and then what holds the cement slab, what holds the house onto the cement slab? We have bolts, that's the bolted. Over here, right angle metal brackets. Then braces, diagonal braces. And then blocking it, putting extra wood in between the vertical uprights, and then paneling it. And what are we trying to do? We're trying to make the vertical and horizontal elements move together. As they are rotated through a circle, we want to have support in all directions and not have the house come apart. Now let me show you one here that I just happened to run into. Here's a house, San Diego house, built in 1971. Specifically, you know, party homes. They built thousands of homes in San Diego. This is a party home. I'm not criticizing them. What I want to look at is changing codes for buildings. So when this was built in 1971, you see that little bolt there? 3/8 of an inch diameter bolt, bored down through that wood into the cement slab beneath it. Now, this house underwent a remodel in 2017. Not a new weight. I mean, it's the same house. It's decorative changes. But by the very fact you apply for the building permit and going to redo the house, do the kitchen and all those things, that also puts you into the retrofit code. And now look what happens. Now, there's a 7/8 inch diameter bolt slid into a deep hole, drilled into the foundation, and that dark gray material around it's a very powerful epoxy. And then we have this device over here that we call a holdfast galvanized iron, very heavy, very heavy. But look what's first off right down here. You see there's another big heavy bolt that goes into the foundation, and then look up the side. There's a dozen or so of these bolts that go into the vertical uprights. So look at that contrast. You know, this is the newer the building, the more stringent building codes they've been built to. So 1971 is not that ancient, but look at the level of earthquake proofing built into the house. Look at the change compared to 2017. Exact same house, two different sets of rules. So as a rule of thumb, newer is better. One other little thing I thought I'd mention here is the soft first story. Now we're back up with the Loma Prieta earthquake here. And of course, that Marina district, very desirable, but there isn't much parking, so they've taken a lot of the first floors and emptied them out to make them garages. Well, when you remove the walls so cars can fit in, then what's holding up the building? Nothing. There's the building. It comes down during the earthquake. Collapse of a soft first story. We get that with houses also. This is in Santa Cruz, near the earthquake epicenter. Same thing, lots of open space on the bottom floor. Well, what's holding up the house? Again, not much. And one other one here from Northridge. Here's an apartment building, the ones where they're sitting on metal poles so the cars can park underneath them. So to visualize this, in your mind's eye, take the parking lot and jerk it to the left. In other words, the ground moved to the left, then the building sitting on the poles basically sat backwards into the lot on top of the cars. So here's this soft first story problem for a lot of buildings. The parking structures have been terrible about that. And again, a lot of them still need to be retrofitted. New ones are built to better codes. Old ones are being retrofitted. And well, just a couple little things at the end here. And the thing that people always want to know, we can't give it to you. So I just say, pick out a beautiful spot like this in Mission Trails Park, enjoy nature, sit back, chill, and enjoy life. Thank you very much. Be happy to answer any questions if there are any. Is earthquake insurance a good idea? You know, it's hard to just say yes or no, because, you know, as we just went through different building styles, and also what are the foundation materials. If you're sitting on a water-saturated, muddy foundation, and is the house made out of brick or out of rock, or is it wood? In other words, building height, materials. Is it on a slope where a landslide might happen? In other words, it depends a lot on the nature of a house. But let me point out another thing along with earthquake insurance. One of the little takeaway messages from the Northridge earthquake in 1994, 10% of the deaths occurred inside people's houses as their own belongings fell on them or were thrown at them. So it's not just the builders that are making things right for us. We have to do things ourselves inside our own houses. Well, since a 6.9 earthquake might occur soon, and soon, remember, that's a geologic term, so soon to a geologist means it might be a century. That's soon to us. But like the pandemic I said to begin with, these things may skip generations, but you never know if your generation is one of the ones that's going to get hit. So what are the things to do to prepare? Well, what I do is relaxed, calm, no pressure, please, but go into each room and look at things and say, what might fall over, what might fall down, move it, fasten it to the wall, make things more secure. Same thing outside. Just look at things and visualize what might fall and then correct those situations to make it better. And then also remember what we teach every year with the Great Shakeout, that your personal safety is the greatest If you're underneath a heavy table or a desk or something where you go underneath it, create a turtle shell on top of you, grab a hold of the legs and hold on and let the shaking go. And don't worry about the family at that instant. If you are running at that instant, you're liable to be the victim and need the problems. Wait out the shaking. Hopefully everybody in the family knows what to do. You can shout out instructions to them, but stay calm, wait for the shaking to stop, come out, and then look to see what needs to be taken care of. In your house, things are good there, then please go help the neighbors. Did the 1933 Long Beach quake show any evidence of jumping south from the Newport Inglewood Fault to the Rose Canyon Fault? That's a very good question. Nothing like that has been shown. Now, the earthquake rupture started in the south and it moved north, but your question is still good because Loma Prieta in 1989 started in the middle and went north and south at the same time. So nothing has been shown on that, but that's a very interesting question. I don't know if a very detailed seismic, running a boat back and forth, doing a real detailed look at some of that, if it would show anything, or if it's too close to shore. What are we talking about here? 89 years, or if too much sand has been washed in and buried it. I don't know, but things like that are certainly worth looking at. Yes, growing up in the Bay Area, people often referred to earthquake weather. Is there any correlation between weather and earthquakes? And this is a worldwide phenomenon. People associate earthquakes with weather. And I think part of that comes from the fact that the big earthquakes are such rare events that when one does happen, you remember, oh, it was freezing. The temperature was only 25 degrees outside, or conversely, man, it was a hot day. It was 100 degrees outside. Well, let me answer it this way. We just talked about several earthquakes. Loma Prieta in 1989, that movement was at 11.5 miles depth and it did not rupture the ground surface. Northridge in 1994, that was 11 miles deep. Long Beach in 1933, that was 8 miles deep. And none of those ruptured the ground surface. My point simply is, if they're starting that deep, if you're starting 11 miles deep and here's the sun or weather coming at the surface, how much of that is transmitted through 8 miles of rock or 11 miles of rock? Essentially none. I'd have to say there's no connection between weather and a big earthquake. Why are so many earthquakes have a 6.214 as depth? Well, these things, the computers kind of have set positions. So 6.214, we're looking at miles. That would be 10 kilometers, I assume we're doing there. So right away when an earthquake occurs, a computer says where the epicenter is, what the magnitude is, and what the depth of the fault movement is. And they're almost never right. They're right in the general sense, but when people look at it, the numbers get adjusted some. So some reason some numbers pop up all the time is they're kind of almost defaults for computers, meaning you were close to that area. Fracking became notorious for causing quakes. Are scientists using that phenomenon to better understand quakes and possibly how to control them? Very interesting question. I could talk on this one for an hour, but I guess I better condense that a bit. First off, fracking, that's pumping water underground under great pressure to cause fractures in rocks to try to get oil out of rocks where it's trapped. There's not enough permeability for the oil to come out. That has been being done since before I was born. So fracking all by itself is nothing new. What's new in the world is they've learned how to drill down and then drill horizontally so they can frack along, a mile-long area like this. And the fracking has so far only caused very minor earthquakes. There are earthquakes associated with the whole process, but not from the fracking. It's the fracturing of the rocks brings up far more water than it does oil. And they have so much water, and it's polluted water now, so they pump it back down under great pressure. And it's that pumping water down under great pressure that causes the earthquakes. And of course, for Oklahoma, it was real famous there a few years ago as having more earthquakes than any other state in the US. And then they made them stop that wastewater disposal, and now we drop back to being more the Oklahoma we know and love. Where's the best place to be in an earthquake if you are not at home? I think, you know, that I flashed that one little message there about earthquakes don't kill, buildings do. Let's enlarge that a little bit. It's not the ground, really, that's going to get you. It's things falling on you. If you're outside, are there power lines over your head? Is there a eucalyptus tree with branches ready to fall? I guess it's a matter of thinking, what is it that could fall on you or hurt you? And that's it. Get into as open a space as possible. If I was out of doors at a park or something, I want to run to the middle of an open grassy area. It's also interesting, though, this is not your question exactly, but I'm going to go back to things like the 1933 Long Beach earthquake. They say that more people were killed running out of those broken buildings we saw, killed by the falling debris while they're running out and getting hit by the debris, than if they'd have stayed inside the building. So again, there's that principle. Don't let things fall on you. If you're in a bad building and bricks are falling off of it, you don't want to run through a rain of falling bricks. Don't let things fall on you or hit you. What is the relative probability of a southern San Andreas quake versus a Rose Canyon quake? You know, that gets us into this topic area where we really have a big zero in terms of knowledge, prediction of earthquakes. We've become so used to that. The meteorologists, the weather people have gotten so good at predicting where a hurricane landfall is going to be or how much rain we're going to get on a certain day. But so far, we have not been able to crack that puzzle. What's going on down there at 11 miles depth? When's that getting ready to break? We just don't know. So in other words, if you look at a map, like I showed, and said, well, here's the San Andreas that moved in 1906, 1857, 1690, you say, which one do you expect to move first? Oh, the 1690. Does Mother Nature know that rule? No, she doesn't know that. 1906 and 1857 may both repeat before 1690 breaks. Now, I'm just talking about the San Andreas, but San Andreas versus Rose Canyon, same story. Don't have any way to know which one would go first. Oh, well, thank you. Great job, Dr. Abbott. Thank you very much. Oh, yeah, love the purple suit. Well, thank you, thank you. I like color. The purple suit is awesome. Well, we're getting off of the earthquakes here a little bit. Fashion statement, okay. All righty. Well, I appreciate your interest and all the questions. And next Thursday, take the day off, huh? Enjoy Thanksgiving, and let's meet again here 2 weeks from tonight. Let's meet again on Thursday, December the 2nd, and we're going to talk about floods. And a lot of that will be going back into the 19th century to see a lot of things that happened then, both with huge floods and with hurricanes, and get an idea of how cities, urban areas tend to magnify floods. Well, I look forward to seeing you all then, and happy Thanksgiving.